So good afternoon, dear students. Can you hear me? Okay, thank you. Thank you. Thank you. Sorry for being late. I'm not in good conditions because of my health situation. So I will try to do the best. For today. Okay, let's continue from our last lesson. Okay, I'm going to share the screen with you. So can you see the PowerPoint presentation? So, okay. In our last lessons, we discussed the so we were at that point relative velocity of points on a separate link. Here the relative velocity of points. We discussed the relative velocity, and below now can we calculate graphically the relative velocity. So the relative velocity of points on separate links may be known. We have such a application here, you see, and for these applications we have this mechanism, as you see in this picture. A, B, C. A is the crank, and B is the slider, and BC is the line where the slider is moving. So, our problem is defined the B2 as a B for the 2. I mean, this is our crank. B2 as point on the link 2, and B4 as point on the link 4. So we define two different points, 2 points, but these 2 points are the same, B2 and B4. B4 regarding the link 4, B2 is regarding to the link B. They have a common point B. So cylinder extends the velocity of B2. So B2 and relative to B4 is along the cylinder. So you may remember from our last lessons, we graphically actually discussed and solved those type of problems. Let's say if this is this AB crank link 2 is turning, let's say, in that direction. So in that direction, counterclockwise. So the speed must be the linear speed must be perpendicular to AB like this. Here is like this. This is the B2, AB2, perpendicular to the line AB, and B4 is mean. This is the slider moving along the CB. I mean, this causes the slider. So then the speed must be in that direction. We know the direction. We don't know the magnitude, but we know the directions. and dBA must be perpendicular to this line, to the B. So then, if we draw the graphic, say the point here from point O, and use this is already must be known, EB2, EB2 must be known because we have to know the RPM or angular velocity. Then we can calculate the VBA and VB2. V2 is equal, as we know from our last lessons, AO times, AB times omega. So that means we know the magnitude and we know the directions. Everything is known regarding VB2. And the VB is let's say like this. VB4 must be like this, parallel to the line here, the directions. But we don't know, we don't know the magnitude. We know the directions, but we don't know the magnitude. So let's take it away here. Okay, we don't know the magnitude. We know only the directions. Direction is known, must be parallel. So okay, and we know also the direction of the VB4. That means VB4 be relative to A, be relative to A. So must be perpendicular to this line. So to this line, and from this end of the vector VB2, we draw a perpendicular line to this here, and we arrive this is VB2. So so it must be, so VB4 so the VB actually on the line, VB for VB4 VB4, and this is the relative motion here. Relative motion perpendicular to that, here in that directions. So VB4 is equal, let's write the equations. VB4 is equal VB2 VB2 plus VB4 about VB2. B2, sorry. B4, B2, that's B2. Okay, B2, that means B4 relative B2. So since we know this, if we the graphic we try to calculate graphically. So we know the VB2 as magnitude and also the directions, and we know the directions of the others vectors VB4 and VB4 relative to VB2. So then using a scale, we can using scale and scale for the known vector. We can measure the achieve the vectors by a graphic. We can by multiplying the scale, we can calculate the value of VB2 and VB4 and also VB4 relative to VB2. So there's an example here. You can solve it as a homework. So as a hydraulic cylinder is extending at a rate of millimeters, so it's given here the rate millimeter per minute to lift the drum. So for the position shown below, determine the rate at which the drum box is rotating. I mean the rotation here, the rotation. So it has to be calculated. So it is like the mechanism we already learned. So this is the I mean the fixed point. We can define the mechanism like this here. So and this is the extension here in that direction. So let's say we can use it like this. So the question is I mean the rotation omega is equal question mark. This is already given. That means VB let's say that this is the A, B, and C. So VB2 is given. VB2 is already given here. So VB2 is equal. The hydraulic cylinder is extending at a rate of millimeter per minute. So that means VB2 is equal. Length is given. How much? Millimeter 3048 millimeter per minute. That means we have to divide by 60. So 60 seconds. And then we can get the millimeter per second, the VB2. And since we know the VB2, so VB2 is, VB2 is known, and VB4, we have to calculate VB4. This is, let's say, the 1, and this is 1, this is 2, and this is 3. So 3, and this is 4 here. So we have to calculate VB4. So VB4 is equal VB2 VB2 plus VB VB2 relative to VB4. So by drawing using the graphical way, we can easily calculate it. So this is the homework. Rest you can do that. So the analytical velocity analysis. So we learn how can we calculate the velocities in 4-bar mechanism using the graphical way. And now, how can we calculate the analytical the relative velocity or the velocity in 4-bar mechanism using the analytical way or analytical method? So the relative velocity method dictates the creation of a vector triangle. So this is the here. So the triangle, this is, as you remember from our previous lessons, this is VA. We can calculate we can calculate as magnitude and the direction. We know the direction. Direction must be perpendicular to the A, let's say the A0, and this is the B and B0 here. So B0. And to derive this mechanism, actually, we should know the RPM of the crank. That means A0A. So the whether the RPM must be known or angular velocity must be known. So in case we know the RPM rotations, we can calculate the omega. You may remember omega is equal 2 times pi n, 2 times pi n. So this is the formula we use to calculate the omega. So then, if we know the omega, and we can also calculate the VA. VA is equal the linear velocity is equal A0 times A0 A0A line times omega. So then using this way, we can calculate the magnitude to be VA, and we know the direction of the others velocities like VB and VBA. So VB, this is the VB here. The direction must be perpendicular to the BB0. So, and VBA, also VBA, relative velocity B relative to A must be also perpendicular to the BA. So we know also the direction using these directions. I mean, so drawing the line parallel direction like this from this point here. So we can find the magnitude. We know the direction, and we can calculate. We can find also the magnitude here. So using the scale, for the VA. But if you know the angle, also, I mean, if you know these angles is shown here, the angle, using the sine law or cosine law, we can calculate also the unknowns. Okay, there is an example here, and you have to solve that for the configuration shown. Analytically determine the angular velocity of the handle that will cause the door to rise at a rate of 120 millimeter per second. In order to achieve this speed, so you have to calculate the requested part. Geometry is given already, and the speed is also given. Okay, so there is another method to calculate the speed for the 4-bar mechanism, and we call algebraic solution for comment mechanism. Comment mechanism, you may remember, we discussed at the beginning of our lessons. Two mechanisms are very common, slider crank and crank rocker mechanism. And slider crank, we had two types of slider crank, inline and offline, and this is an example for offline here. This is general method. If you set let's L1 to the 0, so then we achieve the inline slider mechanism. So you know, we already discussed how can we calculate the geometric parameter like theta 3 here and L4 here. Theta 3 and L4 is very important to calculate. And the gamma also the transmission angle. So, and here, if we know that, we can, in order to achieve the omega 3, we have to calculate the first time derivative of theta 3 and first time derivative of theta 3 is theta 3 gives us the omega 3. This is the angular velocity regarding theta 3, and this is the value here. So, and if we apply first time derivative for the L4, this is the length here, this is the length or position, let's say. The first time derivative of this position gives us the V4. I mean the V4 we are looking for. The V4 is the linear velocity of the slider. So using the analytic formulas and applying the derivative derivation, we can easily calculate the speed. Okay, in case of 4-bar mechanism, general 4-bar mechanism, like crank rocker mechanism. So you see here the geometric dimensions is given. And you may remember we calculated in our previous lessons the length BD and the gamma and theta 3 and theta 4. So applying the time derivation, we can easily calculate omega 3 and omega 4. So the omega 4 gives us actually the angular velocity of the link CD. So there is, before we come to that, I can show you, I did some, so where is it here? Slider crank mechanism, slider inline. So you see the position, changing the position, stroke length, and I have somewhere, not here, huh? So then, okay, what is this one? So, okay, this is what I want to show you. This is the position is changing. Let's say from 0 to the within 360 degrees, the slider crank mechanism. And this is the stroke length. It starts from 0 and arrive the maximum and come back to the initial position in one cycle. That means in 2 pi. So, and we check the velocity of this mechanism here. So this is the velocity V4. This is L4. I mean, this is the stroke changing stroke, considering the rotation angle of the crank and the velocity. Position and velocity is calculated. You see here the position changing stroke and the velocity, and we have here, it's very interesting to check here. We know from dynamics, you already learned that, and the stroke starts from the 0, and here somewhere arrive the maximum speed, like this here, maximum speed, and then arrive let's say the slider, the final position, and stop there and returns. And where it stops here, we have this 0 speed. The speed is 0. So speed is 0. Maybe I can show using a. Can I do that? A clear line. I need a line. So let's use the okay. So this is the line here. We have the maximum speed, and you see the speed is maximum where we have this, sorry, not the speed maximum, sorry. Arrive the final stage, and speed is 0 at that point. Speed is 0. So because from this point, the slider starts to come back to the initial position again. This is the situation. We have here the speed is 0, and speed start against but in the other direction gets its maximum. Here the maximum, and at the end, after arriving the final station of this final position, after arriving final position of the slider, so the speed gets also to the 0. Okay, so you can also use that. You can calculate. So now another topic is regarding the speed for bar mechanism, instantaneous center of rotation. So instantaneous center method, let's say we will use another method that's also very interesting and important. Instantaneous method, say instantaneous center of the rotation. So you see here we have let's say the crank slider. This is slider, and this is the crank and it's the coupler here. So in determining the velocity of points on a mechanism, the concept of instant center. So this is the important part, concept of instant center. So the concept of instant center can be used as an alternative approach to the relative velocity method. So it can be relative, can be used an alternative approach to the relative velocity methods in order to calculate the velocity. This approach is based on the fact that any link, regardless of the complexity of the motion, instantaneously appears to be in pure rotation about a single point. So this is also interesting. So this approach is based on the fact that that any link, regardless of the complexity of its motion, so regardless of its complexity, of its motion, instantaneously appears to be in pure rotation about a single point. So, and which is the single point? So we are trying to find the single point, and it will provide certain, let's say, the help so that we can calculate the speed of any points of this link. This instantaneous pivot here, this is, we will talk about here, this is that. Pivot is termed the instant center. So we call it instant center of rotation for the particular link. So here, that means this particular link 3 is at this instance turning about the point 1, 3. So it's indicated 1, 3. 1, 3 means the link 3 is turning about the point 1. So 1 is, the stationary. But at this instant. So because every link has an instant center with every other link, each mechanism has several instant centers. The total number of instant centers is a mechanism with n links. So we can calculate the total number of instant centers. So there is instant centers for, this is also interesting, every link. So every link has an instant center with every other link. So relative to the other links. Each mechanism has several instant centers. The total number of instant centers is a mechanism with n links. So this is the formula we can calculate that. Total instant center, total amount of instant center. So locating instant center. So where is the location of instant center? In a typical analysis, it is seldom that every instant center is used. However, the process of locating each center should be understood because every center could conceivably be employed. So this is the, for example, regarding the link 2 and 3, the instant center is 2, 3. Because each of them, 2 is let's say rotating relative to 3 about this point, or vice versa. And if we have a gear pair like this here, so this is the instant center here. So 2, 3. That means 2 is turning about the comment. Both of them are turning about these centers for instance. Or if we have like here the slider, and this slider, the instance center of the link 3 is so somewhere in this line, perpendicular to that line. Let's use the column. Okay, it must be perpendicular to the line where link 3 is sliding on that. Okay, and here, if we have like the two curve, like you see here, link 2 and 3, and as a mechanism, the instance center is the 2 about 4s on this line, perpendicular to this line here, to the tangent. So when two links are connected by pin joint, like this here, this is the case. So pin joint like this. The instance center relating the two links is at this pivot point. So this first rule is illustrated in figure A. You see that here. This is the first rule. Second rule here, B. The instance center for two links in rolling contact. So like this here, the rolling contact here, rolling contact. So let's use them. In rolling two links in rolling contact with no slipping is very important, is located at the point of the contact here. So instance center at this point. And 3, the instance center for two links with straight line, like this here, figure B, straight line, two links with straight line. Slider is, straight line slider is at infinity. Infinity, that means on this line here, somewhere, but we don't know. 3 about 1 is at infinity. So the instance center for two links having general sliding contact, like this here, general sliding contact. This is pure rolling, no sliding. So here, this is sliding, rolling and sliding at the same time. So the instance center for two links having general sliding contact must lie somewhere along the line normal to the direction of the sliding contact. So on this normal. So contact must be somewhere along the line normal to the direction of slide. Line normal, this is the normal here. where they have the contact here. This is the contact line, tangent, and this is normal. Somewhere on this line, like here you see 3, 2 along this common normal. So knowing this information, so we can easily find the instance center, and we will learn how can we calculate the speed using the instance center. So there is a theorem called Kennedy theorem. Instance centers that cannot be found from the 4 rules for primary centers are located with the use of Kennedy's theorem. It says that the 3 instance centers corresponding with any 3 bodies all lie on the same straight line. 3. So this is the important information. The 3 instance centers corresponding with any 3 bodies all lie on the same straight line. So on the same straight line. For example, imagine 3 arbitrary links like 3 and 4. Let's say we have here a 4-bar mechanism. We have link 1, 2, 3, and 4. So, and then 3, 4, and 5. So Kennedy's theorem states that instance centers 3, 4, 4, 5, and 3, 5 all lie on the straight line, on a straight line. By applying this theorem, after locating all primary instance centers, all other instance centers can be found. So we can find. Locating the precise position of the instance center can be accomplished by using either graphical or analytical methods. Of course, graphical methods includes both manual drawing techniques and or CAD, computer-aided design. So this instance center diagram is a circle divided into segments, one for each link in the mechanism being analyzed. The segment separates are labeled with the numbers corresponding to the links. So an instance center diagram for a 4-bar mechanism is shown in figure. You see here. Note that the lines in the diagram form triangles. Each triangle represents 3 instance centers. So there's one triangle. So here, let's say 1, 2, 2, 3, and 3, 1, like this here. Or we can say this must be in a line, in a straight line. Or using another color, we can say, okay. So 1, 4, 1, 4, 4, 2, and 2, 1 also must be on the same line. And also here 2, 3, 3, 4, and 4, 2. Like this, we can write like this here maybe. Let's use the column. We can say here 1, 2, and 2, 4, and 4, 1 4, 1 must be on the same line. Or we can say 1, 2, 2, 3, 2, 3, and 3, 1. 3, 1 must be in one line, in straight line, and so on. Like here, formally by lines. Here, for example, let's use the so for example, refer to the figure C like this here, C, and isolate the triangle formed by lines 12, 23, and 13. 12, 23, and 13 or 3, 1. So 3 or 1, 3. As Kennedy's theorem, let's write the same as is indicated here. Okay, here instead of 3, 1, we write 1, 3. Doesn't matter. So 1, 3, 1, 3, and here we can write also 1, 4. Doesn't matter. Here 1, 4. Like here 1, 4. Okay, 1, 4. So 1, 3, 1, 4. Okay, so Kennedy's theorem states that these three instance centers must be collinear, must be on the same line, straight line. So let's have an example and see what we are talking about. So figure illustrates a self-locking brake for a platform used on shipping docks here. So for this mechanism, locate all the instance centers. So draw a kinematic diagram. So this is the kinematic diagram. You know, this is the real picture. Let's say the sketch, and we derive from this sketch the mechanism. This is the mechanism you see here. Huh? So already, so this is the mechanism here. This is the sketch. So these figures illustrate a self-locking brace for a platform used on shipping docks. So, and first of all, we have to draw a kinematic diagram. Kinematic diagram you already learned in our previous lessons. How can we derive a kinematic diagram from a mechanism? Sketch an instance centers diagram. So then the instance centers diagram we have to create and locate the primary instance centers. Use Kennedy's theorem to locate and so on. So the total number of the instance center is how much? So using this formula is about, this is 6. 6 total centers. This is the 6 total number of instance centers. So the total number of instance centers is 6 using this formula. So then let's find it. So here you see this is our mechanism, and we said here we draw our circle where we indicate 1, 2, 3, 4, which are showing the links, and we connect them. Sorry. So we connect them like this. And we have the triangle. like this. Here we can use the triangle. So using this, let's use the color triangle like this here, and this one here, and so on. Huh? So, and we can show the instance centers. Here we write in a table 1, 2, 3, 4. We have 4, and this is we have here with 1, 2, 1, 3, 1, 4. So, and here write 2, 3, 2, 4, and here we write 3, 4, and finish. So that means we have 1, 2, 3, 4, 5, 6. 6 instance centers. So how can we show that? We know that if we use this triangle 1, 2, 2, 3, and 1, 3 must be on the same line. So let's see that 1, 1, 2, 2, 3. 1, which is 1, 1. This is 2, 1, 2. This is done here. This is 1, 2 here. So 1, 2. Let's use another color here. Maybe it's better. 1, 2. This is the one, the point A. 1, 2. And then, so 1, 2, 2, 3. Where is 2, 3? This is 2, 3 here, you see. And the other one is 2, 2, 3. The other one is the 1, 3. 1, 3, 0, 2, 3. So, and this is here. 1, 1, 3. So let's use the other one, this triangle, and use this color here for that. And this is okay. Use that 1, 4, 4, 2, 1, 2, 1, 4, okay, 1, 4. This is the 1, 4 here. You see 1, 4. And then 1, 4, 4. Okay, we have the 4, 4, 4, 3, 1, 4. It's 1, 4, 4, 3, 4, 3, 1, 4, 4, 3. Where is it? 4, 3. You see here. 4, 3, and 3, 1. So here, huh? 3, 1. So on the same line. And then we can write maybe 1, 3, 3, 2. We did it already, huh? So we can say here maybe this triangle 4, 3. Where is 4, 3? Let's use another color. So 4, 3 is here somewhere. 4, 3. 3, 2. 4, 3. 3, 2 is here. And 2, 4. 4, 3, 3, 2, 2, 4. 2, 4 is somewhere here. Also on the same line. You see? Or using this methodology based on Kennedy theorem, we can easily find how much, the amount of the quantity of the instance centers, and also using this the way of drawing circle and the triangle, we can find out which of them are collinear on the same line. So graphically velocity analysis, instance center. Using the instance centers, how can we analyze the velocity? So the instance center method is based on the following three principles. So first, the velocity of a rotating body is proportional to the distance from the pivot point. So this is important. The velocity of a rotating body is proportional to the distance from the pivot point. So that means here, this is the distance here from A to the rotating point A0. And the velocity of the rotating body is this velocity VA and VB is proportional. VA and B for the point B is proportional to the distance from the pivot point. So the second, the instance center that is common to two links can be considered attached to either either link. So, okay, and the absolute velocity of the point which serves as the common instance center is the same, no matter which link is considered attached to that point. So we can calculate the absolute velocity, like here, for example, the point B is here, because point B and point A both of them are turning about the point. Let's say here O is right. It's not indicated. Use here the O, point O, and instance center for the point B and A is O, and the same here also O, and therefore all the points on this body are turning about the point O. So therefore we can let's say any point C, like here, for example, is turning about the point O, since O is the instance center for the body here. So then must be perpendicular to that, like this here. It is C. This is VC. So any point on this rigid body. Okay, so let's have an example here. Actually, we discussed this example, but we use this example for this method. I mean, for the calculation of the relative velocity and the velocities using the instance center. And you may remember, or this is our previous example, the crank and the connecting rod of a theoretical steam engine are 25 meter, 2 meter longs respectively. The crank makes 180 RPM, this is the rotation, so that we can calculate the angular velocity in the clockwise directions when it has turned 45 degrees from the inner dead center position, determine velocity of the position, so angular velocity and so on. So let's come here. So you may remember from our previous lessons that we said, so we can, using the graphical way, we can calculate, since we know the speed of VB, so then we can assign the VB, and the relative B to A, B to P, we know the directions, and we know also the directions of, let's use the pointer, is better. So we know the direction of the relative velocity V, B about the point P. So this is the direction, must be perpendicular to BP. So then we know the direction also of the P because the horizontal. So then by using this information, we can easily calculate VP and VBP, and also any points on these coupler like E and G, we can calculate the absolute velocity. So the method we learned now is the instance center. So where is the instance? Now we are going to calculate the speed of the point P and B, or any point on the coupler BP. So therefore we need the instance center for the link 3. Instance centers, that means at this instant the link 3 is turning about this point. So for that reason, we said that 1, 2, and 2, 3, and this is say here. So this is the example here: 1, 2, 1, 3, 1, 4, and so on. We can use this here. This is the example. Let's write the instance centers. Here. So the instance center 1, 2 is here. 1, 2 is here. Okay. This is 1, 2 here. Huh? 1, 2, and then 2, 3. Where is 2, 3? 2, 3 is here. So 2, 3 is this point here. This point. Okay. And then 3, 1 or 1, 3 is here. 1, 3 is here. So that means if we draw this line 1, 2, 3, 2, and we know that 1, 3 is somewhere on this line. And we know also 1, 3 is also on this line. This is also 1, 4. You see here the 1, 4, and sorry, I have to correct it. So 1, 4, and this is here 4, 3, 4, 3, and this is also 1, 3 on the same line. Here we can write 1, 4, 1, 4, here 4, 3, and 3, 1, or 1, 3 is same. 2, 3, and here 1, 3 on the same line. So if you draw this line 1, 4, 4, 3, and 4, 3, and 1, 2, and 2, 3, so they cross the so they intersect here somewhere, and it's the point where we have the instance center for the member 3, for the link 3. So that means at this instance the link 3 is turning about the point 1, 3. So 1 over 3, like here we say 2, 1. 2 is turning about the 1. Or here 4, 1. 4 is moving on 1. Or this is the absolute velocity. So then we can do the following. we can do following. We can say, okay, use that. So I can turn the angle that we said that is proportional here somewhere. So the velocity of a rotating body is proportional to the distance from the pivot point. So proportional. Based on this reality, we turn this VB 90 degrees in that direction here, and we indicate this VB in that line, and then we can turn also this VP 90 degrees the same directions, and we indicate on that line. And if we draw a parallel from the point here, from this point to this point, parallel to the line PB. So this is the line where all the points, all the absolute velocity of the points on this link have its end. So that means the E point E has also the velocity VE here. So VE, and any point G, for example, must be directed to the center, and the crossing point with this line is the end of the magnitude of the line. So using this method or methodology, we can, this is another possibilities to calculate the relative velocity and the absolute velocity. Okay, so we finished the relative velocity and velocity. I mean the topic velocity, velocity calculation for the mechanism, four-bar mechanism. We learned different type of methodology like graphical method or analytical method, algebraic method, and instance center, and using the instant methodology of the instance centers. So I will finish for today, and I hope next week I feel much more better, and we will discuss the chapter acceleration. Okay? Sorry for being not healthy.
Thank you, teacher. Bye-bye.
Bye-bye.